Hi everybody, that's the first video for diode lectures. We are going to explain p-in junction and semiconductor material. Diode is made of semiconductor material. Semiconductor material have 4 valence electrons. Example for semiconductor material, silicon. And silicon has atomic number equal to 14. It means has 14 proton and 14 electrons. 14 electrons will be distributed around the orbits. The first one will have 2 electrons, the second orbit will have 8 electrons, and the last one will have 4 electrons. The last 4 electrons, they are called valence electrons. So silicon material has 4 valence electrons. Why we are interested in valence electrons in the last orbit? Because valence electrons can be responsible for conduction if we can free some of them to be free electrons. Because as we know, the conductive current, who is responsible for the conductive current? Free electrons. We have other material, also germanium. And germanium has atomic number 32 proton, and it will have also 32 orbits. If you look at the structure for the germanium, the first orbit will be filled with 2 electrons, and the second will be filled with 8, the third will be filled with 18, and the last one will be filled with 4 valence electron. So it is very similar to the silicon. The difference is the 4 valence electrons in the silicon material, it's in the third shell here. However, in germanium, the last 4 valence electrons, they are in the 4th shell. So the valence electrons in germanium are at higher energy levels than those in the silicon. Therefore, it requires a small amount of additional energy to escape from the atom in the germanium. That's why germanium are considered to be unstable at higher temperature, because as we know that the temperature it gives energy to 1 or 2 whatever of the valence electrons to be free electrons and cause conduction. So we don't need to have unstable material. So that's why silicon most of the time is used as semiconductive material. So when you look at the silicon material, and we know that each atom has 4 valence electrons, so we'll find that each silicon atom will try to have another 4 neighbor silicon atoms to share the electrons and to have 8 electrons in its last orbit to be balanced. Let's look at the example here. That's the silicon. We are not going to draw the all orbits 1, 2, 3. No, we are going only to sketch the last one that it has the valence electrons. So that's the orbit. So it has to have another 4 with it. That's the second one. And that's the last orbit. This one. Each one has 4 electrons. So for this one in the middle has 4 electrons. It will be sharing 1 with each. That's 1, 2, 3, 4. So the last 4 valence electron in the one in the middle shared with the other. What about the other? Each one is going to share also their 1 electron only. So this silicon will has 1 electron here and the other 3 in different position. Let's look for the other one, other silicon one. Choose different color. And this one will share one electron with its neighbor, and the other 3 will be with other. For the third one, we'll share one here, and you got the other 3 in different position. The last one, we'll share one here, and the other 3 in different position. So each one will be doing the same, not only the middle, and this one will also, but I mean, I don't have space to sketch the other. So focus on the one in the middle. It has 8 electrons in the valence orbit here, or the valence band, and it has only 4, but I mean, the other 4, they are shared by neighbor atoms. That's, I mean, we call it an intrinsic, means pure silicon crystal. And at the room temperature, if it has sufficient heat, thermal energy, for some valence electrons can escape and jump in the conduction band if it has energy. But if there is no enough energy, the electrons, they are tied together and make this pure crystal. So how can we make the conduction in the semiconductor material? Well, they do something called doping. So what's doping? Doping, it means when you add impurities. What do you mean by impurities? I mean, it means different type of atoms. So if we add, for example, atoms that it has 5 valence electrons, you can make something called n-type. And if you add impurities that has 3 valence electrons, you can make p-type. Example for one material that its atom has 3 valence electrons in the last orbit, boron. Boron has 5 atomic number. So the first one orbit will have 2 and the last will have 3. So it has 3 valence electron. For other type of impurities that has 5 valence electron, like phosphorus, it has 15 atomic number. So if you look for the structure of the atom, we'll have 2 in the first one, 8, and then 5 electrons. So it has an extra electron because, I mean, it has 4 plus 1. So it has extra electron. That will make n-type. And this one has 3, so it's 4 minus 1. So it's missing 1 electron. So it makes whole. So the add, so n-type material is done by adding this kind of material like phosphorus or antimony, anything that has 5 valence electrons in the last orbit, that would be considered as impurities from the type we call donor. Why they call it donor? Because as you see, it has 5 electrons, means it has extra electrons, so it can give 1 free electron. And other one that has 3 valence electron, when you add it to any material, will be missing 1 electron. When it's missing 1 electron, it means there is a hole in the material. It means it's ready to take electron from outside. So they call it acceptor. Like boron, it's an acceptor. And phosphorus, it's considered to be donor. Let's look at B-type material, N-type material after you adding this impurity. Now you have N region and B region and we put it together. That's B region and that's N region. N region has more electrons, the majority electrons. Why has more electrons? Because the material added to the silicon, like phosphorus, has extra electron. Because there's 5 in the end. So this extra electron, if you, of course, you have many atoms of this material, so you have more electrons. On other hand, the p region, they are done by adding the boron, or the material has 3 valence electron, so it's missing. So it has more like holes, the majority holes, because they are missing electrons. So that's, the structure of Bn. So we have 2 region, B region and N region. And once you put them together, you got something here that's called Pn junction. Once this is done, so the electrons on the side, will diffuse to the side, to B region. The electrons from N region will diffuse to B region. Again, N region has many free electrons and few holes. But P region has many holes and few electrons. So when P-N junction forms at the boundary between the 2 regions, free electrons from N region will diffuse into B region to combine with the hole, because there is a hole here need electrons, but which electrons will diffuse from N region to P region? The one next to the boundary, the one in this region, because the far one does not have energy to go all this way to cross. So what happened if from N region the electron want to go here? Okay, you guys just have a closer look. That's electron in N region, and that's hole. Electrons and hole. So this one will cross the region and fill the hole. When the electron, of course, is negative. When the electrons leave its place from N region, it will become positive ion. And when it go and fill this hole become negative ion. The second electron, the same thing. It's negative, but when it leave the region, it will leave behind a positive ion. And it fill the holes, and the holes will have electrons, will have negative. So in the end, you'll find that the region close to the P-N junction, that's the B region, and that's N region, you'll find in the end, in this small region, you'll find it becomes positive charge, and that will be negative charge. Of course, you still have free electron. They are not finished. Just, the one did that just close to the junction itself, and you still have holes in the B-type. So, after that, when you have enough here, cross region, negative, it will prevent any more electrons to cross, because why the electrons will go here? And this is negative charge, and electrons negative charge. It will happen like repulsion force. So it will prevent any more electrons to cross. So no current will go. This will work like a barrier, that it will not allow any more free electrons to cross this region. And this voltage built by this region, they call it barrier potential. Okay. So this barrier potential, this is like electric field between the positive and the negative, because if you have positive charge and you have negative charge, so you have electric field in this direction, and this electric field prevent electrons to go in this negative because of the repulsion force. And this electric field, you overcome it, you got to give voltage to the semiconductor that's more than the barrier voltage. Maybe somebody asks, what is the value of the barrier voltage or the barrier potential? It's a very small region, and it's in silicon. This barrier voltage, we call it V gamma, it's equal 0.7 volt. So you need to put 0.7 volt across the semiconductor to make the electrons overcome this barrier and cross this region. For germanium, the barrier voltage is equal 0.3 volt. And this region, they call it depletion region. Depletion region, why do you call it depletion region? Let's write it nice, clear. This depletion region consists of two layers, positive layer and negative layer, near the junction. Why do you call it depletion? Because this region is depleted of charges, carriers, due to diffusion across the junction. It's all crossed here near the region, so they finished all the electrons near the region only, but the one that far is still there. So that's why they call it depletion. And as you said, that it's a very thin region. So, and to overcome this region, you got to apply voltage to enable the electrons or give energy to electrons to cross or diffuse to the other side. And this voltage, it depends on the material. If it's made of silicon, so you need something more than 0.7 volt. If it's germanium, you need more than 0.3 volt to diffuse. Okay. How we represented the B-N junction? That's the B and that's N. You can have metal contact here. They put metal contact and then you put the wire. And you represent it like that. That's the symbol of diode. This side, they call it anode, letter A, and this side, they call it cathode, letter K. And the real one in the life, this is the diode, look like that. And there's a stripe, a band on one edge. This band used as a guidance for you to know what is the cathode and the anode. It means cathode is very close to this band on the diode, and the other side will be the anode. Well, how can you make the diode conducting current? Okay, that's our BN junction, and you have in the middle the depletion layer or potential, the barrier potential and the contact, and you connect here resistance. If you wanted to conduct current, you put a voltage source in this way. You connect the positive polarity of the voltage source to the anode, to the p-type, and the negative polarity of the power supply connected to n-type or to the cathode of the diode. So if you make it like a diode, so it means that's the way to make the current flow on the diode. The positive connected to the anode and the negative connected to the cathode. They call this one forward bias. Forward bias, it will allow the current to go from the battery through the diode. The diode will allow the current to go through it if we have it in forward bias. Forward bias has two conditions. Number one, the anode is connected to the positive and the cathode connected to the negative but it's not enough. And the voltage bias, this battery, call it bias, should be more than 0.7 volt if you are using silicon. Why we need that voltage? To overcome the barrier potential, so it can give energy to the electron to cross. That's the condition for forward bias, and sometimes we just call it FB. And what happens when you are doing this way, forward bias? It will give energy. The source will give energy enough to free electrons and overcome the potential barrier. So if you just have a closer look, that was the positive and that's the negative depletion region, and you have here holes, well, that's B-type, and N-type you have electrons, free electrons. When you connect, this is to the positive and this is to the negative, so what happened? Sufficient energy will go to the free electrons to overcome this barrier and move into the P region. After crossing the junction, they lose energy because it has energy, but to cross this one, the energy will be consumed for crossing and overcoming this electric field. And they will combine with the holes, because you know that electrons, when go to the holes, combine. So it will go there, and then will be the negative go inside the hole, will change the B region. But the positive polarity of the supply will give energy to make it go and continue its way. So that's how the electronic current will go. Remember, when we say that the electronic current in this direction, it means positive current will be in the opposite direction. Because if you have electrons in this way, and this free electron move to another thing, so it will leave behind holes, right? And this electron will go and jump here to fill this hole, so the electrons comes here and leave behind hole. Then the electrons will go and move here, so the electrons jump in this hole, we have electrons here, and this will leave behind the hole, and so on. So you see, the hole, the electrons moving in this direction, the holes will be moving in different direction. That's why we are saying that the hole's direction is opposite to the electronic direction. So when we say here in this diagram that this is a current, it means not the electronic current, it means the positive current, but the electron is just going in the opposite direction. That's to avoid any confusion. So that's how it will conduct when you connect here to the positive and the negative for forward bias, as explained here. What happens if you make it reverse bias, or what does it mean, reverse bias? If you have the B-in junction in this way, you have the depletion layer, and this is anode, and this is cathode, that's B-type, N-type, and you make it reverse. It means you have the positive polarity of the supply, and this is the negative. So what will happen when you do that? That's called reverse bias, and you can write it RB. And electric symbol will be like that's the diode, that's the resistance, and that's the positive, and that's the negative. So we'll understand here. We have here electrons in N-type in the region, and you have holes in B region. So what will happen? That the depletion layer will increase. Why? Because the electrons will be attracted towards the positive. So when the electrons move in this direction, what will happen? It will leave behind positive. So you will have here positive, more positive. Okay. And this is the negative. So the holes will be attracting to the holes. It will mean when it will leave behind it negative. So what you see now, the depletion layer is increasing. The potential barrier is increasing. And when it increases, the depletion layer or depletion region, when it increases, it will prevent any electrons to cross the boundary. And the diode will be off. So, conclusion, if you want the diode to conduct current, you have to make it forward bias by connecting the positive to the anode. If you want to make it no conduction, you make reverse bias. You connect the positive to the cathode. Here, it will work as a short circuit. So you can represent the diode as a short circuit. Switch and close. In this one, with no conduction, you can represent it as an open circuit. And the current will be zero. That's simply how the diode operates. If you want to look at the characteristic, let's explain how to find voltage current characteristic of the diode. How we'll do this? Let's test the forward bias. We'll get the diode and we have resistance to limit the current, and we'll connect it in the forward bias, and we're going to change the voltage, and we'll put a voltmeter here to measure the voltage called VF, and we add an ammeter here to measure the ampere, IF. And we're changing the voltage of the battery here. This is the bias voltage. And we'll check the characteristic, the relationship between VF and IF. When the voltage starts with zero, the current is zero. When the voltage increase, let's say to 0.3, still the current is very small. When the voltage reach 0.7, if this made of silicon, so I can see here that at 0.7, if I increase it, I'll find that the current starts shooting and conducting. So that's the characteristic in the forward bias. So it means before 0.7 volt, which is the barrier potential, the conduction is very small, its current is not conducting. But once it hit 0.7, as you see, the current will increase rapidly because the material, like a short circuit, will be conductive. And the voltage across the diode will be very small, like from 0.7 V to 1 volt. It doesn't matter how much you increase the voltage, it doesn't exceed the small amount, but the current increasing rapidly. If you can have real thing, this is milliampere, and this is voltage. So that is the forward bias region, the VI characteristic. What about if you do the reverse bias? So the reverse bias, this is the diode, this is the load. You connect the positive here and the negative. We'll put ammeter to measure the current, and we'll put voltmeter to measure the voltage. And we'll change. By the way, it's opposite now. So the current will be IR in the reverse direction and is measured in microampere because it's very small. And voltage reverse because the voltage will be negative on this diode. We change it, or flip it, than the forward one. So we start to increase from zero, no current. And it doesn't matter how much increase, but till you reach a region, a specific value here, you will find that the diode will start to increase and to conduct, but after big amount of voltage. So, but during what you are increasing, the voltage in the reverse bias is not like that. This is in 0.7 volt. But here, you exceed volts, it does not conduct because you are in the reverse. This is very small current. It's a microampere. Till you reach this value at the knee of the curve, this value is called breakdown voltage. So VBR, it's the breakdown voltage. And IR will start to increase rapidly after we reach VBR. But VR, the voltage across that is not increasing rapidly. And you be careful with the diode because we do not want to reach this region or you're going to ruin the diode. So that's, important thing. And we have some value in the datasheet called PIV, peak inverse voltage. It means when you have the voltage in the reverse bias, there is value, a certain value should not exceed it, not to ruin the diode. Of course, BIV is less than the breakdown voltage. It's specified for each diode. That's all for the characteristic of the diode. And next lecture will be how to analyze the circuit that has diode. Thank you.